So now we are going to the first chapter, designing for a static load. I am admitting initially only this chapter, although is there from subject of machine design, but mostly it is SOM itself. Basically, we will be studying regarding theories of failure. So I will take the basics of SOM and then I will explain the theories of failure concept in this chapter. So we'll be starting actual part of machine design. That means actual machine designing thing from the second chapter. Okay. So we'll go to the first chapter. So kindly put the title, make it fast. Design for static load. Okay. So these are the subtopics we're going to study. So we'll study regarding modes of failure, how many types of we'll study regarding concept of factor of safety. Then we see the stress strain relationships and theories of failure. Okay. You don't need to copy these 4 subtopics. So just I'm giving you a basic idea here. What are the things we should be considering or completing here. So we'll go with the definition for a static load. So could you please tell me, new people, all the new people who are attending this lecture for the first time, could you please tell me what exactly do you think or what comes to your brain when you hear about these words, static load? So tell me. So whatever you have in your brain, just let me know. Afterwards, I'll give the correct definition. You can keep it in your brain. So what exactly do you mean by static load? So constant load that does not change with time. Constant load will not change with static load which is in at rest. Okay, so load which does not change with respect to time. So except Chiranjeev Das answer, other people's answer all are correct. But specifically, or if you want to give the exact definition for a static load, you should say like this. So a load which is not changing with respect to time. So that's the definition. But actually, if you want to tell it more specifically, you should say its direction or magnitude. Neither one of them should change with respect to time. So load which is not changing either its direction or magnitude with respect to time is called as static load. Okay, that's the thing here. So in this chapter we'll deal with the loads which are static in nature. So they're acting on the machine element and they're not changing their direction or magnitude with respect to time. So once we complete that part, then we'll be going with the second chapter, which is nothing but designing for the dynamic loads. So there we'll be studying regarding, that means how to do the designing for dynamic loads. So dynamic loads means opposite of static loads, that is the loads which are changing their direction or magnitude, any one of them at least with respect to time is called as a dynamic load. So we'll see the static loading designing in this chapter and dynamic loading designing in the next chapter. That's the thing here. So please write the definition. So load which is applied to a machine element or a mechanical component and which does not change its magnitude or direction with respect to time. That's the thing here. So kindly copy this title of the static load. Okay. So load which is applied on a machine element and which is not changing its direction or magnitude with respect to time. Okay. None of them should change with respect to time. So such type of load is called as a static load. Okay. So we'll discuss designing of machine elements with respect to static loads in this chapter here. Okay, so before going further, I would like to explain to you what exactly do we mean by changing of a volume of a machine element. Okay, then afterwards I will explain you what exactly do we mean by changing of a shape. So changing of volume a little bit easy to understand, very easy. So changing of volume means here, if you have a machine element which is little bit of this size and looking like this one initially, now we are increasing its volume or decreasing its volume. So you are applying some loads in some particular fashion and you are achieving this state. So it has changed from this condition to this condition here. So it has changed from this condition to this condition. So we are increasing its volume. So volume is actually not constant. In this case, what you are doing is you are increasing its volume by keeping mass as constant. So when mass is constant but the volume is changing, then automatically that means that its density is actually changing. If volume is increasing, density will decrease, or vice versa. That means if the reverse thing here, if the density is decreasing, if the volume is actually decreasing, then density will increase here. So volume is not constant here. This implies that density is also not constant in this thing here. So change of volume means this thing. Kindly copy this. So change of volume. So in the process or in the situation where change of volume is occurring, when mass is constant, so density will not remain constant at all. This is the thing which you must be taken into consideration here. Why mass is not constant? I haven't said that I'm taking out some mass from the element there. So mass is remaining constant there. Okay, I'm taking that condition. I'm not doing anything else. I'm applying loads and decreasing its density, that's it. Or increasing its volume here. Okay, so now we are going with the next one, that is change of shape. So change of shape means here, so change of shape means it will be looking different before the application of load and after the application of load. So here it is looking almost similar to the before the application of the load and after the application of load also here. Understood? So it is like this change of shape, somewhat like this one here, in this one here. So if some load is acting and making it to go to some other form, so I am making it to go to some other circular form like this, okay, some other form here like this one. So it will look a little bit different here. But the necessary condition in this change of shape is you must keep its density to remain constant. So keeping density constant, if you are making the body to change from one form to other form, that means it will not be looking similar before the application of the load and after the application of load, then that should be, that means this is the condition which, that means basically I would have to say that this is the condition which you require in changing of its shape. So if this is the condition, mass is constant and density is constant here, so this implies that in this condition, changing of shape, you will be keeping your volume also to remain constant. That's the thing here. So I guess the concept is clear. So please write down these two things in a clear way, because generally we take those things in a general way, but we should take everything, we should learn everything in a technical way. So we should be exactly defining those things. Changing of its volume means, so changing its volume change is occurring means density is also not remaining constant. So changing of its shape means here we are keeping density to remain constant, that means we are keeping volume also to remain constant. So these are the things which you have to keep in mind here. Sir, how static load is changing volume? Given a definition for given a definition for static load, that load which is not changing its direction or magnitude with respect to time. So don't think that if I want to elongate or compress some material, I should be going on changing its magnitude of load. So for some block is there here. If I apply a load which is equal to some 10 Newton suddenly, so 10 Newton will create some force. So 10 Newton will create some stress, and that gives us elongation. Okay, so constant magnitude of loads are sufficient to create change of shape or change of volume. So don't get confused with that one. You can change, you can cause these things. So that means you can change volume or shape by using dynamic loads or static loads. But here I'm telling you what basically you understand by change of volume and change of shape. That's it. Yeah, any change of shape. Yeah, anyways that is obvious from there, Jagdev, right? It's obvious from there, nothing to say. So mass is constant, density is constant, automatically volume also will remain constant. Understood? So we are done with these two things here. So kindly keep these things in mind: change of shape and change of volume. So basically, I would like to why actually I have made you people to understand regarding these two things is I would like to make you understand or learn clearly the definitions of the terms which you see on the secondary slide. There are some terms which are having names like deformation, distortion, dilation, like that. So generally we take those terms as synonymous and use use one term at the place of other, but actually they are having different definitions. Understood? So that's why I would like to make you people to understand those terms. That's why I'm putting in front of you people here. So most important or most main objective is I would like to make you understand the definition of distortion, because distortion is a theory of Ariel is there. So if you don't know the definition of distortion clearly, then understanding other thing is will be tough, or you'll be getting misconceptions with a particular thing. Okay, so to have a clear concept regarding that one, you should know the definition of distortion. So to understand the definition of distortion thoroughly, I have explained you regarding the change of shape and change of volume. So these are terms here which you think or which you take them as synonymous: deformation, distortion, dilation, disruption, fracture, all these things here. So mostly you might not be taking fracture with these earlier four terms or the upper four terms as synonymous, but first four terms generally you try to take them as synonymous, or you think them as synonymous. Okay, but actually speaking they are having differences like this. Deformation means you should
Thawarikeri main road.
experience both volume and also shape change. So if it is experiencing both volume and also shape change, then we call it as deformation. So simply the actual technical definition is deformation means its volume and shape both must actually change with respect to both must actually change here. So distortion means only shape change. Okay. In the same way, dilation disruption means only volume change. Okay. So fracture. So fracture means basically, if a machine element is there, we call it has experienced fracture only when it has broken into at least two pieces. So we should be able to see two separate pieces of the particular element. So that should be possible. Then only we can be calling that one as a fracture. Understood? So fracture should be that thing here. So the biological fracture which we study, that like if a small crack is happening on a bone, so we'll say it's actually a fracture. So that's not the thing which you'll be taking in. That's not the meaning of the word fracture which we'll be considering in the subject of machine design. Okay, so failure we'll be studying in a very detailed way in the coming slides. So if a machine element or anything is there, if a gear is there or a flywheel is there, if it is not able to perform its objective perfectly, okay, if it's not able to perform, for example, gears are there. So gears are basically used for power transmission. If I am applying loads in such a way and breaking one of the gear teeth, okay, one of the gear tooth. So if one of the gear tooth is actually broken, it's left with another remaining number of gear teeth, then it cannot transmit the power smoothly as it was doing earlier. So it is not actually performing its function perfectly. So that means it's actually got failed. So failure is that particular term here. So kindly write down all those definitions here. So deformation means volume and shape change and so on. So once you complete that, please let me know. When there is change in shape and volume, which occurs first? Whenever apply some load, okay, actually in strength of metals we studied regarding incompressible materials. Okay, so I said that Poisson ratio of isotropic solid materials will be varying from 0 to 0.5. Okay, so we don't have exactly 0. That means we are having 0. Some non-zero value. Okay, so that's actually a cork, and 0.4999 like that as a rubber. So we don't have exactly the member which is having Poisson ratio 0 or 0.5. So all the materials are in between these two values. Okay, so all these materials, okay, so exactly if it's not having Poisson ratio as 0.5, for example, if the material is having 0.5 as a Poisson ratio, then it will experience only shape change, because incompressible materials will not be experiencing any density change. So whatever is the load acting on the material, we can't change the density. So whatever the shape change I have explained you, only shape change will occur. So anyways, we don't have any perfect incompressible material or perfect rigid materials like that. So if you have any material, it will be having a Poisson ratio value varying from 0 to 0.5. So for those materials, okay, whatever materials we see on earth, okay, if you apply the loads will be acting in such a way, that means if the loads are in a general way I'm telling you here, definitely they will change both shape and also volume. If you want to change only its volume, then you have to apply the load in this way. Like if it is a cube, I'm taking simply cube here to make you understand very thoroughly. So if it is a cube here, then you should create same stress in every direction. So sigma x, sigma y, sigma z, all are equal to sigma here, and all the other shear stress component tau xy, tau yz, and tau xz all should be equal to 0. So this is the thing, or this is the loading condition, or only volume change. Okay, so it totally depends on the way the loads are actually acting. Okay, so generally we can say if a load is acting on a real material, definitely at the same time both volume and also shape change will occur. Okay, so I will explain regarding these things in a very detailed way in the coming slides. So if you want, you can recapture the concepts of hydrostatic stress components and duodetic stress components. So hydrostatic stress components means actually they are responsible for the part of stresses which are responsible for changing its only volume. Duodetic components means responsible for only changing of its shape. So all these concepts comes. So in a general way I can say if a load is acting on a component, it will change or basically deform it. Deformation is basically it might be having change of volume, shape, or both. In general, we say both are actually occurring. That's the thing here. And in deformation, will shape change occur first or volume change occur first? Okay, so we got the answer for that one. So I guess everybody copied this thing. Now let's go ahead. I guess everybody are thorough with basic definitions of stress and strain and all these things. Okay. Can I go ahead or not? Stress and strain definitions. Everybody. Please everybody delete all the definitions whichever you have in your brain regarding stress, strain and everything. Okay, so I'm taking a new explanation. I'm giving a new explanation here. So basically stress means the actual definition of stress. I'm writing it here. You can copy from here. So stress means basically resisting force. First of all, I will write down the definition. You can after that I will give the definition. So stress definition here. Resisting force acting on the material So resisting force acting on the material per unit area. Sorry, resisting force induced inside the material. Resisting force induced in the material per unit area of cross section. So this is the actual definition of stress. You copy this definition of stress, and once you complete this, I will give the explanation here. Yeah, Mayank, please wait. Just copy the definition first of all. Let me give the whole explanation for stress, and afterwards you can ask me the doubts if you are not clear. Okay. So please wait till then. Okay. So what is the resisting force here? So if I am applying some force on a body like this, so I am putting some cylindrical body, you can take it because tensile members would be looking like that. So for our better understanding, we will take it as cylindrical body only. So this cylindrical body is experiencing a force in this way. So this force is like this, and so if I am making this body to experience a force like this, then what's happening is it will be moving with some acceleration based upon Newton's first law of motion. Okay. Understood. But if I am making this body to experience net force to become zero, if the net force is becoming zero in this material here, so this is not meant to, the body is not meant to move in that direction, it's not meant to move in this direction also. But as this body is not a perfect rigid material, because we don't have perfect rigid materials in day-to-day life in our on earth, so what happens is internally the body will be experiencing some resistive force in opposite direction like this. So if I am just trying to stretch the body in tensile direction, then it will be experiencing in compressive way here. That means this force will try to make the body to come to the original position once the forces are being disappear here. If I am trying to compress the body, this will be in reverse way. So that's the thing here. So let me show you the other condition also. If I am trying to compress the body, the force is compressing here, then internal resistive force will be in this way here. Okay. So the internal resisting force will be equal to its particular external applied force also, because the body is in equilibrium. Net force on the body is equal to zero. So the body is not meant to have any movement in forward x direction, positive x direction or negative x direction here. So if you take any cross section here like this one, so at any cross section the forward force should be equal to backward force. That's why the magnitude of the internal resistive force and also the external applied force will be equal to, both will be same here. Now when this is the condition here, so when the equilibrium condition is there, we understand or we see that internal resistive force is being produced here. So stress means basically this internal resistive force per unit area of cross section. So this internal resistive force is acting on area of cross section A. Okay, so then stress is equal to, given by simply sigma is equal to P by A here, and here also sigma is equal to P by A here. But here, as the external applied force is acting in a tensile way, so we'll give sign as positive for this one here, and for this one, as it is acting in a compressive way, we'll give a sign to -1 here. Okay, so anyways, these two things are easy to accept, the sign thing here. So always remember that the stress means basically the load acting, that means the internal resistive force produced inside the material per unit area of cross section. That's a basic definition of stress here. Now, to create stress, this internal resistive force should be there. If this internal resistive force is not there, that means if you take this condition where it is experiencing only one force here, the body is not in equilibrium, because equilibrium means net force should be equal to 0. So when force is there, acceleration will be there here. So F, internal resistive force, is equal to 0 here. F is equal to 0 here. So in this case, stress is equal to 0 here. So sigma is equal to 0. Understood? So we see that internal resistive force is the driving factor to experience the stress. Understood? So in this case, we see the internal resistive force is produced only when the body is in equilibrium. So the necessary condition for the material to experience the stress is it should be in equilibrium. So please write the definition here. Okay, I'm writing the definition next term here. So the body should be in equilibrium. The body should be in equilibrium. The body should be in equilibrium to experience stress. Dear Rahul, please wait. Okay, I will take the vector quantity, tensor quantities, all these things, etc. in the second chapter. Okay, or sorry, in this chapter only. But please wait. I will explain you each and every doubt regarding all of your basics. Okay. It's not 2F. It is simply F by A. Sorry, it is. I should be putting it as P here. I should be putting as F. Okay, you are asking regarding disruption dilation. Yeah. Disruption dilation, actually the terms actually come from the way the loads are actually acting. So disruption is basically if explosion is occurring. Okay, explosion is occurring and once a solid body is becoming into a small, very small particles, which like total disruption has occurred there. So in that context, the terms are used there. For example, if only volume change is occurring, okay, so volume, if component is there, so it is actually experiencing a finite amount of volume change. So I can take that or I can call it as dilation, okay. But if suddenly some blast is occurred, okay, so some thermocol piece got blasted into some small balls, okay. So there it becomes very tough for me to find out the final volume. So might we can take it as volume got become infinite. So to take out, that means in that situation it's better for you to use disruption rather than using dilation there. So everything got disrupted there. Understood? So basically volume is occurring, but the way the volume got changed is a little bit different. So indefinite cases were there in disruption and definite cases were there in dilation. That's the difference here. So that's enough for you people to understand regarding the difference of disruption and dilation. I was thinking that you were asking regarding distortion and dilation. That's why I told you people to go to the terms there. I guess now the definition is clear. Although the definition for stress is based upon internal resistive force, but the sign is given based upon the external applied force itself. Okay, you can say in other way also. This internal resistive force is acting in positive x direction. So I can take positive sign regarding this thing also. This thing is acting in negative x direction. I can take sign with regard to this thing also. So that's why we don't go with the sign based upon direction of forces, because external applied force is also acting in positive x and negative x direction. Internal resistive force is also acting in negative x and positive x direction. Okay. So we'll take the sign if it is tensile in type. Okay. Positive sign if it is tensile in type. Okay. If we take the sign as negative, if the external force is compressing the material. So compression and tension both are actually a little bit different in practical material, in real materials. That means the way the material is behaving for those two loads is different. So we have to distinguish between the both of them. So this negative sign or positive sign will help us. Okay? Am I clear to you, Mayank? Why can't a body experience stress when it is not in equilibrium conditions? Rahul, I said, we need to have internal resistive force. Okay? So when you make a body, that means what's happening is basically when you don't keep the bodies in equilibrium and when the which is experiencing a non-zero force, non-zero net force and experiencing acceleration here, all the elements, that means I guess chemistry wise you can say elements, okay, for example iron elements are there, okay, aluminum elements are there. So all those molecules, elements, whatever are there, they are moving with a constant acceleration in a forward motion or in the direction of force according to Newton's laws of motion. So there is no some reaction between those particular all those molecules or elements there. Understood? So when there is no reaction, we can't experience stress. So like this, in a molecular way, at molecular level, we can say stress is not there. But anyways, in mechanical engineering, we don't go into that term of depth there. So for time being, you can understand in that way here. In this case, as you are making the body to be in this situation, you are making the body to stretch or get compressed here. So the molecules are actually coming near, pushing over each other or getting pulled away from each other. So that internally something is happening. So that's giving rise to some stress. Okay, the material is experiencing some type of stress means stress itself. Some type of depression is experiencing there. Understood? So in a general way, you can say, like if I'm getting huge amount of work to do in a less amount of time, so a huge amount of mentally load is there on me. Oh, I have to complete that. I will complete the target by 5 o'clock before the office is completed. Okay. So such type of thing here. So as the material molecules are coming near to each other, they are being forced to go away from each other, coming near to each other. So something is happening inside the material. Okay. There's nothing but stress here. In this case, there's nothing happening here. So that's why you can't say stress. Stress is there in this scenario here. Am I clear to you? Yes, Rahul, your answer is correct. What you are saying is correct. Every material, okay, I haven't taken how it will be different in ductile material, how it will be different in brittle material, okay. So to experience the stress, simply the metal should be in equilibrium. If it is in equilibrium, it will experience stress. That's the only thing here. No matter whether it is ductile or brittle, okay. So in the given body, if magnitude of force is changed, then will be stress or not? Magnitude of force, okay, you are saying magnitude of force is different. Okay, Chiranjeev, I understand your question. That means if you have a condition where the element is experiencing some non-different values, like for example 10 Newton in forward direction and 5 Newton in backward direction, then you might be asking this question. I think This is the thing here. So here also stress will be there, but stress will be 5 Newton by area of cross section. Because although it's experiencing non-zero force, it's not in perfect equilibrium. We call it as partial equilibrium condition because 10 Newton force is being cancelled out. So 10 Newton force forward and 5 Newton force backward here. So 5 Newton force is being cancelled out here. So 5 Newton force by area of cross section is nothing but stress. So anyway, this 5 Newton here also, this 5 Newton is actually in tensile direction. There's a tensile stress here. So anyways, we will not be going with these partial equilibrium conditions. So in this level, we'll be going with only perfect or simply the basic equilibrium conditions itself. Okay? Am I clear to you? So I guess I have cleared everybody's doubt here. So stress is this thing here. So I guess everybody had copied this thing. I'm rubbing the board. Now we'll go with the definition of strain. So strain means basically a simple definition only, nothing to understand in deep. So strain means change of dimensions to the original dimensions. I'll actually write down here, you can understand from here itself. So strain means basically ratio of, so strain means change of dimensions to original dimensions. So if you go with the linear strain, L-I-N-E-A-R, linear strain. So linear strain means change in linear dimensions. Change in linear dimensions to original dimensions. Change in linear dimensions to original dimensions. So if you go with the volume strain, so volumetric strain means change in volume to original volume. So like this thing here. So these things are very easy to understand. You can copy this. So strain means is of two types, linear strain and volumetric strain. So just copy these terms. Why area strain is not? Bhavanagar, there is no technical term like that. Okay. So I can't say that sun rises in west. Okay. So like that, no area strain is there. So we use the term only thing that percentage area strain. That's it. So percentage area, that's it. Percentage change in area. We don't use the word strain for changing of the area, that's it. Okay, I'm repeating once again. Somebody asked that why don't we have area strain? So we don't have the term, that's it. So we have a strain definition for linear strain and volumetric strain only. We don't have it for areas. We don't have it for area strain. So we simply call it as change of area by original area, that's it. Okay. So it's over, everyone. The some subjects are like that. Okay, some subjects what happens is like they are a little bit complicated. Okay, for the first time when you hear, you feel very tough to digest. For example, you go with thermodynamics. I don't know whether thermodynamics is over for you people or not. So if you go with topics like entropy, if you're going with topics like availability, so for the first time when you hear in the lecture, where the lectures are going on like frequently, like every Saturday, Sunday, you might be having lectures and all these things, then what happens is basically you feel very tough to digest. So there, having spirit to learn or having enthusiasm to learn will be very, very less. Okay, but you have to cross that level. So subjects like SOM, machine design are very much related to reality, like where you can understand the things. Understand things means where you can imagine those things in your brain. So if I say about entropy, then you can't understand whether to imagine entropy as an energy, entropy as a fire. Okay, entropy as something like, so what is the thing actually you have to imagine in your brain? It will become tough. So subjects are different. So we have to take everything into consideration. So you should not be blaming that particular subject. So you should be blaming the subjects only in terms of weightage. If a very, very tough subject is having good amount of weightage, you should be blaming for that one. Understood? So you just have to invest energy in that way. So SOM machine design, like you can learn in the classroom itself. But for theory of machines, thermodynamics, etc., you have to practice well. And for SOM also you have to do practice there. So you can take these things into consideration. Rahul, please don't worry. Lateral strain, longitudinal strain, those are basic things. Like for example, if I take a tensile member like this, if I am creating a stretch in this longitudinal direction, length direction. So whatever change of length by original length I take, that's nothing but longitudinal strain. So whatever the degrees of diameter that occurred, change of diameter to original diameter will become lateral strain because it is in the lateral direction to the longitudinal direction. Understood? It's a lateral direction to the length direction. That's why we take it as lateral strain. So those basic things you can understand. Clear? You don't need to worry regarding that one. And did 31 years in Tom, is it sufficient? Yeah, it's more than sufficient, Mayank. You go with every subject. I'm not telling regarding only my subject. You solve all the 31 years previous gate questions from this, for all the subjects. Okay, so, make sure to, don't go with 5 marks questions into the depth. Okay, so because like in 1995 up to 1995 you're having 5 more questions also, that might be a little bit lengthy, so please don't waste much time on those questions. So go with 1 marks and 2 marks, those will be sufficient. Understood? Okay then, so this is over here, strain thing is over. So I will go with other terms fastly because we have invested good amount of time on these things here. So the next term which you have to study is normal strain. So normal strain. So normal strain means basically, I am giving you the definition directly here. So if the load which is creating stress basically, okay, because you have to apply some external load, keeping the body in equilibrium to experience or to create stress. So if the load is acting perpendicular to area of cross section, so stress induced inside the metal is called as normal stress. If the load is acting parallel to area of cross section, stress induced should be called as shear stress. That's the thing here. So here normal stress, normal stress. First of all, let's go with normal stress. So if you have a member and the load is acting perpendicular to area of cross section, so stress will be normal stress and shear stress. So shear stress means if a machine element is experiencing load parallel to area of cross section. Okay, so load perpendicular to area of cross section, load perpendicular to area, load parallel to area. Understood? Load parallel to area of cross section. Okay, so I think these things you can easily remember. Make it fast. Hemant, you people don't worry regarding completion of syllabus. Okay, we'll complete everything. Only the thing is like based upon the availability of the faculties, what are the gaps, whatever you are seeing, those things are occurring. But we'll make sure to complete the syllabus 100% and before time. Okay, you don't need to worry regarding that one. Okay. So it's over, everybody. These things are done. Okay. So now the next things I'm directly telling you here. Normal strain. Normal strain means whatever strain occurs because of normal stress. That's nothing but normal strain. Whatever strain occurs because of shear stress. That's nothing but shear strain. So because if I am applying force on this body in this way, then this will become little bit like this one here. So this angle gamma, whatever we are showing it here is nothing but shear strain. Understood? So this is how the terms shear stress, shear strain, normal stress, normal strain, all these things are actually defined here. Now, we have to go with the main part here. So if you have a tensile member like this, okay, I'm taking a cylindrical shaft only. So it's having original area as A0, original length as L0 here. I'm applying some load P. So these loads are keeping it in equilibrium, so it will experience some stress here. So this member is experiencing some stretch like this. So final area because of this load P is nothing but area is A1, length is L1 here. So in this case, stress is normal stress or shear stress? Please tell me. I'm going with very simple questions now. Stress is normal stress or shear stress? Normal stress. Okay, so very simple thing here. So sigma, so what is the formula? P by A0 or it is P by A1? New people, please tell me. P by A0 or P by A1 here? So here you can go with either of them. Okay, but there is a difference in going with each one of them here. Basically, if you are willing to find out stress or strain, but if you are taking initial dimensions, because by the application of load, definitely dimensions would change. So if you are going with initial dimensions, those values of stresses and strains, okay, I am writing it here clearly. Initial dimensions, INITIAL, in bracket A0, L0. So if you are going with initial dimensions, so in that case, the stresses and strains are called as conventional values. Conventional values or engineering values. Okay, so till I complete the first chapter, for the old people who have attended the SOM class, so many things will be repetition. Okay, I can't help you with that one. Okay, so I have to make all the new people to understand every bit of the concept thoroughly. So I will be going with all the concepts here. So you just patiently listen here. So initially, if you're going with initial dimensions, A0, L0 to find out stress or strain, so those values of stress and strains are called as conventional values or engineering values. So conventional stress, conventional strain. Okay, engineering stress, engineering strain, all are actually same here. But if you're going with instantaneous values, So if you're going with instantaneous values, that means dimensions are A1, comma L1. So if you're going instantaneous values, so those should be called as true stress. Okay, so true stress, that means true values basically. So true stress, true strain terms will come. So true values. Okay, so example, true stress, true strain. True stress, true strain, like this. Okay, so I'll explain you regarding them here. Copy it fast. So if you're going with initial dimensions, so the particular corresponding values of stress and strain are called as conventional values or engineering values. And if you're going with the instantaneous values of dimensions, A0, A1, L1, etc., so those are called as true stresses or true strains, or true values basically. Okay, I think there's some video audio lag here. So I haven't completed much of the syllabus today. So we are at the initial itself, basic definitions of stress and strain only. I'm taking the basics of SOM to understand the concepts of machine design thoroughly. So I'm going with, I'm done with the basic definition of stress, strain and all these things. So I'm going with true stress, true strain, conventional stress, conventional strain and all. So you can see here. So other people, is it over? Make it fast. Other people, is it over? Okay, I'm writing the board. Okay, now listen here. Generally, in real life applications, it is very easy to have initial dimensions. That means before the application of load, what are the dimensions we are having? So before the application of load on the tensor member itself, we can measure the area of cross section, we can measure the length. Okay, so we have the dimensions there. But once the loading is started, so we can't use the whatever the measuring instruments are there to find out the instantaneous values of stress, instantaneous values of areas of cross-sections and instantaneous values of lengths there. Okay, so although in tensile loading conditions we can find out the change of length by using extensometer, but we can't find out the instantaneous area of cross-section very easily. So at a sudden, if it is breaking, so we can, if you are near to the machine, if you are near to the particular element, that loading member, then we can experience some damage or we can experience some injury. So it is not preferred to go near to the machine element while it is experiencing loading. So we can't measure the areas of cross-section very easily there. So what we're going to do is we're going to get some relation between these conventional values and true values, because it is easy to get initial dimensions. So we can easily calculate conventional values of stress and strain. Okay, so true values, because actually that is the correct value of stress or the correct value of strain the material is experiencing. So we're going to get some relations between conventional values of stress and strain with the true values of stress and strain. That's what we're going to find out here. Understood? So we are actually deriving for a material which is actually incompressible material. So I guess you people have completed this fluid mechanics. So what exactly do you mean by incompressible fluid? Could you please tell me what's the definition there? First of all, everybody give me answer for this incompressible fluid or incompressible material. So incompressible fluid means basically density is remaining constant. So throughout the flow, density of the fluid is remaining constant. So in the same way, incompressible material means density is remaining constant here. So if the material's density is constant and anyways mass is constant, so density is equal to constant. So this gives you that volume is remaining constant. So initial volume V0 is equal to V1. So initial volume is equal to area into length, area of cross-section into length here, and final volume is equal to A1, L1. So from this one we will be getting the answer that A0 by A1 is equal to nothing but L1 by L0 here. So we actually going to derive the final formula for a perfect incompressible material. Okay, so in center metals we have studied that for a perfect incompressible material where its density is not remaining constant, density is remaining constant, its Poisson's ratio value is equal to 0.5. Okay, so I'm just making you to recapitulate regarding that point here. Okay, so here some doubts are there here. Some people are saying that we generally measure the value of stress by using by the value of load from time to time there. Okay, so there basically what we are doing is we are increasing the value of load very slowly. Okay, so I said that static loads means the loads which are not changing their magnitude direction with respect to time, but we want to see how the variation of stress, variation of strain is there when the load is actually when the load is changing its when the load is at different magnitudes. So to see the variation of stress and strain at different values of load, so definitely we have to change the value of or the magnitude of load there. So if you suddenly increase the load, it will become a dynamic load, and that loading condition will become a dynamic condition, and it will become tough for us to evaluate. Okay, so we increase the load very slowly, very slowly, such that load magnitude is actually increasing very slowly, such that internal resistive force will be produced with equal amount of magnitude. So internal resistive force will be produced with the equal amount of magnitude there. Okay. So that means if we increase the load magnitude very slowly, that means we are giving that amount of sufficient time for the material to create its own value. That means to create equal value of internal resistive force. Okay. If you increase very fastly, so outside force, that means as this moving body is moving with some acceleration. Okay, we are increasing very fastly there. It is getting stretched with some acceleration. So if you take a small element, okay, small element which is of some thickness here, it is moving with some acceleration. Okay, so that means this direction force should be higher and this direction force should be lesser. So what happens is this force will be higher and this force will be lesser. So if you increase very slowly the magnitude of load, then we give sufficient amount of time for the internal resistive force to become equal to this externally applied load here. Understood? Understood everybody? Okay, so that's the thing here. So increase the load very slowly to keep to make this body to experience only static load only. Understood? So any other doubt is here? Okay, so anyways for this thing, where density is constant, we are getting this relation here. So let's use this relation to get the answers. Now we take this our tensile loading member to be having initial dimensions as A0 and L0 and final dimensions as A1, L1, and it's experiencing a load P here. Now if you want to get conventional stress, so first one here, conventional stress. So conventional stress sigma. So conventional stress sigma here, simply it is based upon initial dimensions. So load P by A0 here. Understand? So now second one, conventional strain. So we denote it by epsilon here. It is change of dimensions to original dimensions. So final length minus original length L1 by L0 here. So this implies, so epsilon is equal to this one here. So this implies we can say that epsilon is equal to L1 by L0 minus 1. We got this thing here. So from this implies that L1 by L0 is equal to nothing but 1 plus epsilon. So L1 by L0 is equal to 1 plus epsilon here. So we got the answer that L1 by L0 is equal to 1 plus epsilon. But from here we know L1 by L0 is equal to nothing but simply A0 by A1 here. So we write down this thing also. L1 by L0 is equal to 1 plus epsilon is equal to A0 by A1. So this is the answer here. Okay. So we got this thing. Now we are going with the third one. That is true stress. So true stress is sigma bar. Okay, true stress is sigma bar here. So true stress, okay, so we should be taking instantaneous dimensions. So true stress, I'm putting it as sigma bar. It's not a standard notation, by the way. So P by A1. But we can't get the value of A1 immediately. So we go on writing this thing. So P by A0 into A0 by A1 here. So P by A0 is already known to us, that is sigma, conventional stress. A0 by A1 is equal to nothing but simply given as 1 plus epsilon. Okay, so sigma of 1 plus epsilon. So sigma of 1 plus epsilon here. Understood? So once we get conventional stress and conventional strain, for incompressible material we can easily evaluate the value of true stress by multiplying this product as sigma of 1 plus epsilon here. Now we are going with the fourth one, that is true strain. So true strain, I'm denoting it by small e here. So true strain here, basically strain means change of dimensions to original dimensions. But here dimensions are going on changing from, length is changing, going on changing from L0 to L1 here. So initially length is L0, okay, and finally length is becoming L1 here. So what we're going to do is, we'll take an intermediate state at which length was something L, and at that instant, for a finite amount of infinitesimal amount of time, very small amount of time, suddenly length is changing by dl. Okay, so parameters are not constant here, so we'll take a intermediate state where length is suddenly changing by dl here. So if that is the condition, we'll be getting true strain formula as integral of dl by L from L0 to L1 here. So integral of dl by L, L0 to L1 here. So dl by L, so it is log of L here. So ln of L1 by L0. So ln of L1 by L0 here. Ln of L1 by L0 here. Okay, so what are the final formula I'm writing here? Or whatever I have wrote here. Final formula, whatever I have wrote. So these are valid for only incompressible material. Because I am using this relation, so this is valid for only incompressible material. But first formula, whatever I have written, first formula, whatever I have written here. So simply like true stress is equal to P by A1, okay, and true strain is equal to integral of dl by L. So this is valid for any material, irrespective whether it is incompressible material or not. Okay, so we are using this relation means it's valid for only incompressible material. Understood everyone? So please copy this thing fast. So I will give you a question in the next slide. So the correct answer for this question is B. So it's very simple. The value of true strain produced in compressing a cylinder to half of its original length is. So you take initial length as L0 is equal to L. Final length is equal to L by 2 here. So we have to get a true strain, right? So true strain we have it as ln of 1 plus epsilon, or we have it as integral of dl by L, L1 to L1, L0 to L1 here. We go with this formula which is very easy. So integral of dl. So dl by L from L0 to L1, that means log of L final by L initial. Okay? Or you take it as initial everywhere. So L final is equal to L by 2 and initial length is equal to L. So this gives you ln of 1 by 2 or minus log 2. Minus of log 2 here. So log of 2 is equal to 6.69. So minus 0.69. The correct answer is B here. Okay. So we're having the answer as B here. It's a very simple question. So what are the questions whichever they have been asked in the GATE examination were almost similar to like this. So you can get the answer very easily. Okay, and one thing you have to remember is if they don't say whether to go with whether to consider the material to be incompressible material or not. So in a default way you go with considering as incompressible material. Okay, so by example, if you see this question, if you are not considering this material to be an incompressible material, then your answer would be if not considering this material to be an incompressible material, not an incompressible material, then you could not be getting the answer as B here. So you have to consider as an incompressible material, then only you will be getting the answer. Okay, so correct answer for this one is B here. Okay, now we have to go with stress strain curves to understand the concept of failure very thoroughly. So we'll be going with 4 types of stress strain curves. Kindly please copy the list, the name of this list here.